It is for me, as is the conventional opening of a seminar, a privilege and a pleasure, in this case, doubly justified to introduce our speaker of today. He was here already 2 years ago, and everybody is still talking about his talk. Anyway, he is known by all of you, Professor Frank Wilczek. He did his degree in Chicago, the PhD in Princeton with Gross, and later he spent a few years in Princeton, went to California, Princeton again, and MIT. So he goes for decades, no? The decade of Princeton decade, Californian decade, MIT decade, and the future we don't know whether he will be, because he can go almost wherever he likes. We are very happy to have him here. He is, of course, also the 2004, I think, Nobel Prize for Physics for his work in quantum chromodynamics. He's one of the key actors in the Standard Model. Sometimes people attribute the Standard Model to the electroweak, but really we should not forget the outstanding and beautiful, elegant, and profound work that Frank Wilczek with Gross and Politzer did. In addition to that, he is a deep thinker in many fields, but can talk about philosophy, as you will see. And of course, he talks about general aspects of science that very few people can do with the clarity and elegance he does. Of course, I don't want you to take my word for it. I choose Dyson, one of our heroes. I know it's his hero too, but he's hero of many people here. And Dyson writes beautifully well. And if Dyson says what he said about the writing and knowledge of Frank, is because he really deserves it. It's an honor and a privilege for us, and thank you for coming, Frank. Thank you very much.
Thank you so much. So this talk should be considered as part of the ontology conference going on. I'm strictly an amateur in philosophy, maybe not in physics, but anyway, I do think that there's a grand historical tradition of physics informing philosophy and vice versa, and I think although it's somewhat lapsed or loosened in recent decades, it's time to get back together. So, in that spirit, I'm going to talk about some unexpected, to me, intersections between physics and philosophy. This is very personal to me because one of my great heroes and teachers, although I never met him, was Hermann Weyl. When I was a student, I studied very closely his book on philosophy of mathematics and the natural sciences. Had a paperback copy which has fallen apart, but I've repaired it, and I still treasure it. And Weyl thought of himself as carrying on the tradition of Leibniz, whose view of the world was very much influenced by philosophical ideas and vice versa. His philosophy was very much influenced by the revolutionary discoveries in science happening during his lifetime. So let me start. So this is going to be a discussion of several topics that traditionally have been topics of great interest to philosophers, where I think physics has something interesting and important to say. I'm going to start with the problem of induction. That's usually associated with David Hume, who posed it as a problem that instances of which we have had no experience must resemble those of which we have had experience, and that the course of nature continues uniformly the same. This is, of course, part of what makes science possible, and yet can't be derived by pure logic. And Hume was very much troubled by that tension. Of course, it really can't be derived by pure logic. One could imagine worlds in which the laws change from place to place or from time to time. Historically, most cultures have thought that's the way the world works. You could also imagine that if someday artificial intelligence is embodied inside computers and programmers get to make up the rules of how the world works for those intelligences, they might make the rules change as a function of time. They might make things change as a function of place. If you play Super Mario World, you do find that the rules change from time to time and depending on where you are. But not in our world. And although we can't derive it, this uniformity, we can relate it to other things, ground it more deeply in our general understanding of the world, and be very specific about its profundity. And physics has a lot to say about that. Uniformity in time, uniformity of the laws in time, is embodied as a principle of symmetry in the foundations of physics, the symmetry under translations in time. That is, no matter when you start your clock, once you start it, the laws will run the same according to your clock. This is deeply related in modern physics to the principle of conservation of energy in a way that I don't think has been absorbed completely intuitively. Certainly I don't know a completely intuitive explanation that doesn't appeal to advanced principles of Hamiltonians and quantum mechanics, but there's a profound general relationship between symmetry and conservation laws, technically known as Nernst's theorem, that means that the law of conservation of energy and tests of the law of conservation of energy are at the same time tests of the law of invariance of nature under time translations. Similarly, uniformity in space is related to conservation of momentum, and every time you test the conservation of momentum, you're testing this principle of uniformity in space. So although we can't derive those principles, we don't have to separately postulate for every day that the laws are the same as the previous day, or that in every position the laws are the same as in previous positions. We can make a couple of grand sweeping assumptions that are in the nature of assumptions about the symmetry of physical laws that get to a lot of Hume's problem of induction. These principles derive much of their power from locality. That is, we can discuss what's happening in our region without paying too much attention to what's going on very, very far away. If we did have to pay a lot of attention to what was going on very, very far away, then different places wouldn't really be the same because they'd be subject to different influences from the environment. So if astrology were true, we'd be in trouble from this point of view. We'd have to worry about distant objects, and we couldn't rely on the laws being the same. We couldn't make inductions, at least not very simply, without paying attention to the whole rest of the universe, which is usually impractical. And locality, in turn, depends on the propagation, the finite limiting speed of propagation of signals. If signals could arrive anywhere infinitely fast from everywhere in space, we'd be deluged. So it's very important that they take time to propagate. And the fact that forces fall off with distance, so that the influence of distant objects in either space or time lessens with distance. Some of those don't lessen very quickly. For instance, light spreads like with a 1 over r squared law, and if you fill the whole universe uniformly with light sources, the number of them per unit radius grows like radius squared, and so the total influence would be infinite. This was the famous Olbers paradox. So some forces don't fall off fast enough to ensure locality in a strong sense, and we need an additional principle or additional explanation why the night sky isn't uniformly light, and the explanation is connected to the finite propagation speed plus the finite age of the universe and its expansion, that distant objects the light hasn't reached us yet. Also, the universe is bigger, so the light is spread out more. Also, early on, there weren't stars, and so forth. So, what I want to emphasize here is that although we can't address, as a matter of pure logic, this issue of induction, we have a very rich physical picture of what it depends on and why it is true in the world, that we can relate to other ideas and ideas that in principle we can test, like conservation of momentum and conservation of energy, and of course the whole Big Bang cosmology. And importantly, another foundation that allows us to make progress in reasoning about the world and taking lessons from the past and extrapolating to the future is what I call the digital nature of matter. That matter takes only a finite number of forms, that atoms here are recognizably in the same have the same character as atoms in Andromeda or other far, whereas Andromeda itself, for instance, is quite different from our galaxies. And if that weren't true, if it weren't true that atoms and molecules have the same properties no matter where they're found, chemistry wouldn't be possible. And actually, if you look at where that comes from in the fundamental laws of physics, it's a rather complicated story that makes chemistry as we know it possible. One step is that we have to have building blocks which are the same everywhere to get started. And why, for instance, specifically, is an electron here the same as an electron in Andromeda or elsewhere in the universe? And the way we understand that now in the foundations of physics is again related to symmetry, and in fact related to the whole complex of ideas around quantum field theory. So the indistinguishability of the building blocks of the fundamental particles comes from the fact that those particles are really excitations in fields that fill the whole universe, which are more fundamental objects. And the fields have symmetry under space and time translation, which means they have the same properties everywhere, so that disturbances in those fields, namely electrons or quarks if they're quark fields, or photons if they're electromagnetic fields, that those have the same properties wherever they are found and whenever. That gets us started with the little building blocks, but atoms and molecules are more complex composite objects from those building blocks. If we start building, say, the solar system out of planets, it could have been built in many different ways with different numbers of planets, and in fact now that and different sizes of the different planets, different positions of the different planets, and in fact now as people are actually examining solar systems around other stars, they are finding a tremendous variety. But for atoms, it's not that way. For molecules, it's not that way. Why not? Well, the deep explanation is very contingent, has a lot to do with the details of how the quantum mechanics and physics works, and I think has two crucial steps. One is what I call quantum censorship, which is the fact that if you consider a quantum mechanical object, say a hydrogen atom, its low energy states are discrete, so that to get from its very lowest energy state to anything else, you have to inject a finite amount of energy. The same thing for atomic nuclei. You have to inject a much larger energy to change anything about an atomic nucleus if it's in its lowest energy state. So that means that if you supply less energy than that, it's not like a solar system where if you nudge a planet a little bit, it changes position a little bit. If you nudge it a little bit, it doesn't change at all. It has a kind of digital character. So, for instance, in particle physics nowadays, we debate whether particles are secretly strings. You might think if they were strings, it should be pretty obvious. They would wiggle around and would have very different properties than if they weren't strings. But if the strings are in their lowest energy excitation state, and it takes enormous amounts of energy to get them to do anything else, they might as well not be strings at all. They might as well be just point-like particles, and that's quantum censorship is what makes it possible for structure to be hidden. But it is important that you, for the thing to behave as an elementary object that has only one state and no internal structure, so to speak, that you can see, that you don't supply enough energy to take it into the next highest energy state. So, for instance, if you supply enough energy for a hydrogen atom to get out of its ground state, you start to see that, in fact, it was made out of a proton and an electron, and you can make a model of it. If you supply enough energy, it dissociates into the proton and electron, and it's blatantly obvious that it was not an elementary object, although at low enough energy, it does look like an elementary object. I call that sequestration. And there's a fairly elaborate story about how sequestration actually works, so that in the ordinary course of events here on Earth at fairly low temperatures, chemistry works in a straightforward way. The next thing I'd like to talk about is the question of identity versus sameness, not for personalities or people, where I know identity is a very popular subject in philosophy, but in a much simpler context of particles and elementary quantum mechanical objects. Sameness here is often called indistinguishability. It's a very sharp notion of sameness, that they're absolutely the same, that there's no telling one from the other. So, I referred to this already with electrons, that electrons have not just similar properties, but exactly the same properties, no matter where they're found. Leibniz thought that wouldn't be true. One of the fundamental principles of his metaphysics was what he called the identity of indiscernibles, which, more or less in his words, was the statement that two things could not differ only in number, because if there were two things, that the only thing that were different about them was that there were two, they would actually be one, because there would be no way of telling that they were two. But that's not true. Physics adds a rich, new, and surprising perspective on identity and sameness. It's a sharp thing. I'll elaborate on that in a moment. So things can be absolutely rigorously the same, and that will have different implications than even if they can be very, very slightly different. And consequential, Specifically, the world has usually been divided into bosons and fermions. Bosons are particles such that if you have two of them, that are indistinguishable bosons, they not only can but like to obey the same, to be in the same quantum mechanical state. So for instance, that's why in a laser beam, photons, which are bosons, all want to be absolutely the same color and moving in the same direction. Whereas fermions, typified by electrons, obey the Pauli exclusion principle. They cannot occupy the same quantum state. And that's largely responsible for the hardness of matter, although atoms consist largely of empty space. Because the electrons don't want to be in the same quantum mechanical state, they refuse to be compressed. Recently, we've discovered and are exploiting for technological purposes that you can make artificial particles, anyons, that are neither fermions nor bosons, but sort of interpolate in between and have other richer behavior when you exchange two identical anyons. Well, that's another seminar, but I wanted to let you know that studying identity and thinking about what's possible in the quantum world has led to notions that impact experiment and seem to be starting to impact even technology. One more thing that's notable to say about these issues of identity is that fermions and bosons sound very different as apples and oranges. However, one important speculation that's guiding much research in particle physics and searches at the LHC is that at a deeper level, bosons and fermions are actually things you can relate by symmetries. Specifically, you can have what's called a quantum dimension, such that if you move in the quantum dimension, what happens is not that you change position in a conventional sense, but you change from a boson into a fermion if you were a boson, or you change from a fermion into a boson if you were a fermion. And if you construct the theory correctly, you can have equations such that flipping the quantum dimension doesn't change the physical laws. Of course, it changes. maybe that's a statement about supersymmetry. The computer is on and just fine. It's the projector. Something went wrong with the projector. Okay, well, maybe I don't think I should proceed, but maybe this is an opportunity to have questions. If you want to have some questions while we wait, are there? Yeah.
Is there, or can you think of any simple explanation for the connection between spin and statistics?
Well, it depends what you mean by simple.
Well, I mean, at the level that you're speaking now.
No, not really, because even to define them carefully enough to make a relationship requires a little bit more groundwork. But you know, I'll tell you what the connection is, for better or worse. Okay, that if you look at space-time trajectories of particles, so you look at their world lines, okay, and you look at the space-time trajectory of two particles winding around each other. So or more specifically, you produce a particle and its antiparticle, and produce a particle and its antiparticle. exchange the two particles, and bring it all back together and annihilate. That gives a certain topology of the world lines. And that topology is the same as the topology of taking a particle and taking the particle and antiparticle, rotating the particle by 360 degrees, and bringing it back together. So that second one is a measure of the spin. The first one is a measure of the statistics. Since they're continuously related, if you assign a discrete property to one, it has to be the same as in the other. So fermion goes with spin 1/2, and boson goes with spin 1. So you can draw it in pictures, but it takes quite a bit of explanation to explain what the pictures are. But there are pictures and intuition that go with it. Okay. Yeah.
Just a stupid question. Dyson, who spoke so fantastically about you, said that the kind of a floor of physics is full of dead fundamental theories.
Yeah.
Do you expect that the theory of everything that will unify all the existing forces, and you will have, as Hawking says, the full picture?
No, I don't expect that. Not anytime soon.
When will you feel that you are satisfied with the way you represent the picture of the world and the fundamental forces right now?
Well,
I would say that what you're telling us right now is the truth.
Well, it would be tedious to preface every sentence that I say with, maybe this is not true. But that's implicit. I mean, eventually, however, having said that, the foundations of physics are grounded in tremendous amounts of experimental data and experience, and it's cumulative. So although I think Dyson considerably overstates it when he says so yes, occasionally theories have to be discarded, but it's like you're building a cathedral, and eventually sometimes you have to throw away the scaffolding that supported some of it.
So may I ask you the question, do you expect the superstring theory would be discarded or would be supported?
Well, that remains to be seen. I think superstring theory in its present form is clearly not taking us there. I think we need some, but I think it's teaching us something, and a deeper understanding will very likely refer to superstring theory in some form. Yes.
What experimental evidence would you need to proceed further on?
Oh well, I mean, certainly.
Is it available in the nearest future, from your point of view?
Well, we will be learning from the Large Hadron Collider, the LHC, that's operating at CERN right now, for sure about supersymmetry, or it could very well be discovered. If not, well, that'll be very disappointing. So that's one thing. But there are also fundamental experiments in cosmology going on that could, for instance, give direct evidence for inflation from gravity waves, so a sort of super Big Bang in the very early universe. And then there are opportunities for surprises as people make extremely precise measurements, even outside of these very extreme conditions. So one thing is to look at very big objects, another thing is to look at extremely high energy, another is to look very, very carefully at things in earthly laboratories. And all of those could give new information. And we could discuss specific ideas, but that's several seminars. Okay, so back to supersymmetry. I'll just say a couple more words about what these quantum dimensions are, because it's fun, and really very, very simple but profound. Well, I should say the starting point is simple. It gets very complicated very fast, but the starting point is simple. So what is a dimension in the ordinary sense? For a physicist or mathematician, a dimension in the ordinary sense is something that's described by numbers. So a dimension going this way is you have a certain distance this way or that way, and that's a dimension. If you have 3 dimensions, you need 3 numbers. And ordinary dimensions are described by what are called real numbers, the numbers that are familiar to work with and obey laws like x times y equals y times x. Okay. The quantum dimensions are also described by numbers, but they're described by numbers such that x times y equals minus y times x. That's the big difference. One aspect of that is that x times x is always 0, since x times x is minus x times x. And roughly speaking, that means if you make 2 steps in the quantum dimension, you fall off. So the dimension is very small. You can only go forwards and backwards. Okay. That's why it looked like just a sheet. And one sheet has the particles that are fermions or bosons. The other one has their partners that are bosons or fermions. Okay. So, spaces and universality. Leibniz was, and many of the classical philosophers were, of course, very interested in the structure of space, and had ideas that the world was made out of discrete objects that occupied parts of space that excluded one another from the part of space they were occupying, so hard, impenetrable spheres, and just emptiness in between, or else not really emptiness, but monads everywhere, occupying every point. We don't think anymore that that's what points are. We have a much more flexible idea of what points are and how they figure in physical theory. This is so traditionally, nowadays, points are just labels for what happens if you make a translation in time. You move time from one label to another, or space, you move the label from one place to another. So points are just labels for telling where things came from or are going in these transformations in the fundamental laws. And this is a seminar I hope to give very soon here, or I've been given once before already in Poland, that I think our notion of what a point is subject to negotiation. In quantum mechanics, you can pull points apart and put them back together, and spaces that are topologically different can actually look the same quantum mechanically if you allow more general operations. So I think this question of what is a point that has occupied philosophers for a long time is undergoing renovation, and but even before that, before the renovation, in current physics, the picture of atoms in the void doesn't begin to do justice to how we fill the universe with the structures that we need in modern physics. Much attention has been given in recent years to speculations about extra dimensions. I'd like to emphasize that those are interesting, but in fact, physicists have long been flexible, creative, and successful in making use of additional dimensions. So the world is bigger than usually realized. In fact, in the standard model, we use internal spaces that are, again, additional numbers used to label structures in the physical world. The difference between these internal spaces and the conventional idea of extra dimensions is that some of these spaces are such that some particles can move in them and other ones can't. And in fact, the nature of a particle is tied up with its location and its ability to move in the extra dimensions or not. So the difference between a quark and an electron is that there are dimensions that describe the color degree of freedom in which quarks are located and can move. They move through space, but they also, ordinary space, but they also move in these internal dimensions as they change from one color to another. Electrons don't have that particular property, so they don't enter that color space, but just propagate along. And this sounds like some fantasy or whimsy, but this is what the equations that we use successfully to describe matter actually look like. And in fact, almost all the many of the key properties of elementary particles have to do exactly with their ability to move in these extra spaces, and the difference between different ones is exactly where they're located in the extra spaces. So different colors of quarks, for instance, are differentiated by where they are in this color space. And the other difference is that these spaces are fundamentally not related by symmetries to the ordinary space dimensions, whereas the popular extra dimensions that are still speculative are ones that originally had the same properties as the three dimensions of space we know about, but got folded up. So we had it broken. The symmetry is broken, but was originally there. Nevertheless, I actually find it more imaginative and more appealing, these spaces we already have, than the crude idea of taking bigger space and folding it up. And it also has the great advantage of being true, not speculative. Anyway, here's a picture of extra dimensions. And you have to imagine the quarks can move in this extra dimension, and the difference between different quarks is where they are in these extra dimensions, and the fact that it's a quark and not an electron is precisely that it's free to move in these extra dimensions and not just along the plane. So space is much richer and more structured than conventionally realized. Another aspect of that goes back to the bosons and fermions, but particularly the bosons. Many particles can occupy the same position. In modern physics, the idea that atoms are impenetrable, and if one atom is in a place, the other atoms can't be there, is just not true. We're very flexible about what we allow particles to do, and we learn from nature what's required. In any case, the dimensions in the sense of things moving are three if you count the ordinary space dimensions, plus time if you want to consider that as a dimension, plus these internal dimensions, which some particles but not all can access. But all that is dwarfed in a sense by the arena for quantum mechanics, Hilbert space, which is a description of the state of the world or subsystems of the world that uses labels with many, many numbers. In fact, sometimes Hilbert spaces we use are strictly infinite in dimension. Even to describe very small systems, you need large Hilbert spaces. So that, for instance, if you want to describe the state, the quantum mechanical state of just 5 spins, which can be up or down, you need 2 to the 5 dimensions to describe their possible states. Even if they can't move, but just flip from up to down, that's a space of 32 dimensions. Then if they can move, it gets infinite. If they're 6 spins, it's 64-dimensional times infinity, and so forth. So Hilbert space is really, really big. This might make you feel very small. And that's sort of continuing a trend that goes way back in the history of science and acquisition about the nature of the world. We seem to be growing relatively smaller and smaller. Copernicus taught us that the Earth is small compared to the solar system. Darwin taught us that time is enormously larger than everyday life would suggest. Hubble taught us that even the solar system is tiny. And nowadays, people are even thinking that there's a multiverse that extends beyond what we can practically access by observations, where far away in the multiverse, the laws of physics might look quite different, and so forth. And nowadays, you can even see the Earth looking small from the moon. And imagine how we look in the galaxy. And realize that there are many, many galaxies, even in small slices of the sky. So, makes you seem very small, maybe insignificant. On the other hand, I'd like to share with you some striking wisdom, I think, from a remarkable philosopher who I encountered in my studies. This is Frank Ramsey, who was a prodigy at Cambridge in the early part of the 20th century. He contributed extremely significant work in pure mathematics, in economics, as well as in logic, as well as in, well, that's what I meant by mathematics, yes. But there's a whole theory called Ramsey theory, which stems from his work in combinatorics. And nevertheless, despite the fact that he died at the age of 26, didn't quite reach his 27th birthday, he was also a very large person, and you'll see why that's relevant in a moment. Anyway, I'd just like to share with you his perspective on this issue of smallness. So I'll just read this, because it's so pretty and eloquent. Where I seem to differ from some of my friends is in attaching little importance to physical size. I don't feel the least bit humble before the vastness of the heavens. The stars may be large, but they cannot think or love, and these qualities which impress me far more than size does. These are qualities which impress me far more than size does. I take no credit for weighing nearly 17 stone. For those of you who may not be familiar with the English unit of a stone, it's 14 pounds, and a pound is 454 grams. Anyway, you can calculate what this is in kilograms. I'll leave that as an exercise. He goes on, my picture of the world is drawn in perspective and not like a model to scale. The foreground is occupied by human beings, and the stars are all as small as 3 penny bits. I don't really believe in astronomy, except as a complicated description of a part of the course of human and possibly animal sensation. I apply my perspective not merely to space, but also to time. In time, the world will cool and everything will die, but that is a long time off. Still, at its present value, at compound discount, is almost nothing. Nor, so you see, he was an economist as well. Right? Nor is the present less valuable because the future will be blank. These thoughts, I can't help but remark, are very much in the spirit of locality that we get from physics, that the influence of faraway things, although they may be vast, is actually quite limited here in our neck of the woods. Besides, from another point of view, we're actually quite big. We learn that in the micro world, there are enormously small structures that are rich and powerful. Fractals give a tangible sense of that, but the laws of physics, well, in some weak sense resemble fractals, but do have the common feature that they have enormous richness in the micro world underneath the visible macroscopic behavior, somewhat hidden by the quantum censorship and sequestration, but we can try to work around those things. Hilbert space is vast and gives many possible alternative histories that are all realized in the micro world. And perhaps most interesting and exciting is that nowadays physicists, quantum engineers are starting to explore this micro world in a constructive way, to exploit the vastness of Hilbert space, to do things that we're interested in, and take advantage of the fact that although we're very big, very small compared to the galaxies or the universe or the multiverse or even the solar system, we have access to a vast space that we're bigger than and we can manipulate, and the opportunities are, in a practical sense, unlimited. So thank you for your attention.
So now Professor Wilczek will answer questions. I'm sure there will be many.
Somebody's got to break the ice.
It takes the first one.
Yeah.
Pedro? Pedro, wait for the microphone because it will be paid.
So you have stressed the importance of locality for
Yes.
a theory. Does it mean that a fundamental theory of nature should be local or can be non-local?
Well, non-local, in principle, could be anything that's not local. So that is a priori much more likely than local, which is something very specific. On the other hand, at present, it's not a question of can be, it's a question of what physical law actually looks like. The successful description of the world that we've built up over centuries is heavily built on the principle of locality. That's been a guiding principle that led us to was very helpful in guessing the structure of the standard model, and it works. So if you're going to introduce non-locality into the foundations of physics, it has to be done in a very tasteful, tricky way so that you avoid what seems to be mountains of evidence for fundamental locality in the description. Yeah.
Well, thank you. And yet, quantum mechanics seems to be non-local in some important respects.
Well,
so
it's in a
what's
different
your
sense. That is.
Yeah, but I mean, there is an element of non-locality in quantum mechanics at the level of correlations and such.
Right. Okay. This is in danger of getting very technical very fast, but I doubt very much we have fundamental disagreements, but there can be disagreements about the use of words. And since we're describing very unfamiliar circumstances, familiar words may have subtleties in their use. So, for instance, maybe very likely you're referring to things like the EPR, Einstein-Podolsky-Rosen situation, where measurements on a wave function here affect measurements on a wave function there in subtle ways. And that's a form of non-locality, and is consistent with physical law, but it's a very weak form of non-locality. And I wouldn't call it non-locality at all, because you're not really sending signals or information non-locally. Those spins, or whatever they were, had to be correlated at some earlier point and then taken away from each other. So very crudely, and well, you're probably going to get annoyed, but but this is oversimplification. But very crudely, for non-experts, it's as if you have a pair of socks that one is red and one is green. And you give people one sock, two people one sock, or you send one sock over here and one sock over there in a box, but don't tell which one it is. And then somebody measures way over there that he's got a red sock. The other one will know he has a green sock. Immediately, doesn't take a finite amount of time for the message to propagate. I wouldn't call that non-locality in any real sense. Now, quantum mechanics, that's an oversimplification of the quantum mechanical situation, but I think it really is the heart of the matter. Yeah. Yes. Yeah.
You are really well educated in philosophy.
Well, thank you. I'm strictly an amateur, but
now
how should I say? I know almost nothing of philosophy after 1920 or so, except for Hermann Weyl.
That was exactly my question.
All right.
You've already answered it. Thank you. If you are aware of any works in philosophy that date a bit later.
Only dimly, no.
So no Kuhn, no...
Oh, well, Kuhn, okay, call that philosophy.
Okay,
I call it history.
History,
yes.
History of science. Okay,
right.
Your idea, at least about what he wrote about the way science develops. Do you agree with his kind of interrupted?
Okay, so I should say, when I say that I'm strictly an amateur, well, I am strictly an amateur, that's for sure.
Yeah, but you are the one.
I studied deeply Hermann Weyl. I studied deeply Bertrand Russell.
Yeah.
I've studied much less deeply later philosophers, Quine and Putnam and so, but also, just sort of, I don't know, well, I don't know if this is interesting in my biography, but I've also studied sort of just for interest. Not that those are all philosophers who deal with these kinds of questions about the fundamental. And there's a different set of philosophers who talk about scientific method, sociology of science, history of science. Okay, there I have much less confidence, Kuhn and Popper, I have much less confidence in my own judgments. But, I mean, I know from deep experience how science actually works. And, for instance, I am very unfond of the falsification criterion. I don't think that's how things work at all. When we find a theory that's beautiful but false, we don't throw it away. We try to find a way that it could be true. For instance, we're looking for truth. We're not looking for falsity, to put it crudely. Kuhn, I think, again, I haven't studied it in depth, but I think the idea that there are two different things, normal science and revolutionary science, I think that can easily be overstated. I think normal science is always being renovated, and sometimes big changes occur gradually, so that it only becomes obvious, so to speak, when the lava breaks through the surface, and that looks like a revolution, but actually it's been boiling up under the surface for a long time. And anyway, I mean, I'm very, very, very against the idea that many people have taken from Kuhn's work, that that scientific theories just get discarded. That never happens, or certainly almost never. People build on things. So even Copernicus, okay. Where was Copernicus coming from? Well, Copernicus was a careful student of Ptolemy and the accumulated data and parameterizations of that data, and he noticed that several numbers in Ptolemy's system that had no reason to be equal are actually equal, and then he looked for a way of accommodating that. So, yes, it was a big change, but it was very much rooted in what came before, and of course the whole attitude of understanding planets and so even in that sort of most favorable case, I think it's oversimplified.
So I have a rather non-technical question. So these all complicated concepts and this advanced body of knowledge about the strings and the particles and the fundamental particles and fundamental interactions appear to fall far away from our common experience from the point of view of an ordinary man, although they address very fundamental questions related to our own origin. So it seems to me that at this time it's only accessible to fewer minds equipped with very elegant mathematics. And is there a way to bridge this gap, or it is going to be a very elite?
That's what I'm trying to do, and I plan to spend significant time in coming years trying to do exactly that. I should say there are two very different things. I mean, if you want to master this material in such a way that you're in a position to advance it, then that requires a very high level of mathematical knowledge and a lot of work, patience, and even then you probably won't do it. But there's another thing, which is, can you understand enough to enrich your picture of the world and also make it more accurate? And for that, you don't need anywhere near as much mathematical knowledge. What you need are sort of the right metaphors, also patience, honesty, and then you can appreciate the insights that we get from these very esoteric investigations. I should also say that, quantum mechanics may seem very esoteric, but it's what makes your iPhone work. And there'll be more things like that. Yeah.
Near the end of your talk, you, as a side remark, you said there's one direction to the big one, and another direction to the small one, and progress there, and you added high energy as a third dimension of the third. How about complexity? This would be again another direction. Would you just add that, or would you say that's implied and doesn't deserve mentioning?
No, I wouldn't. God, I can get in trouble that way with Pedro, especially. No, complexity is absolutely another axis of investigation, and it's a little bit hinted at here. That it's one thing to have the equations; it's quite another thing to exploit them creatively. We also take input from the external world to see what kinds of intermediate concepts are useful in describing things. So complexity and coping with it is very much a creative enterprise and a frontier of physics.
Thank you. Marvelous talk. Somebody said, or it is said, that nothing makes sense outside evolution. So my question
nothing
is...
in biology. Quantum mechanics certainly makes sense without evolution.
No, the question is, does the theory of physics, the standard model and so on, make sense outside the arisal of Homo sapiens? In other words,
Yeah.
You believe...
there are no Homo sapiens out in Andromeda or on other planets, and yet they work according, as far as we can tell, they work according to the rules of quantum mechanics happily without, and the standard model and physical law without, they would work pretty much the same without Homo sapiens. And the universe got along quite well without us for most of its history. And, well, as I say, if you measure just by length of time and volume of space, human beings individually and collectively are not very impressive. On the other hand, if you use locality and you yourself are a human being and you interact with human beings, they're plenty big to control lots of resources, and that's our world.
So you said in your talk, and I totally agree, that the way science was going was to take man away from the center of the universe. The Earth stopped being the center of the solar system,
right.
And Darwin told us where man stood, somewhere in the middle. But for a while, starting from Bohr, but also pushed for a long time by Wigner, perhaps in despair of interpreting quantum mechanics,
yes.
They started to bring man back to the center of physics.
Right.
That human consciousness was somehow needed. I think that's profoundly wrong.
Yes.
So I wanted to know your opinion.
No, I agree. Yeah, it's profoundly wrong. I don't think anything we've learned in the meantime, since the days of Bohr and Wigner, has given support to their view that really consciousness has an important role in quantum mechanics. That we've learned more about consciousness. We've continued to test quantum mechanics very delicately and in other domains, and consciousness is still not understood, really. Well, not even close at a molecular level, but there don't seem to be any clear barriers to understanding it at a molecular level, and more is being understood about how brains work and memory and so forth. And in quantum mechanics, some of the things that disturbed Bohr and Wigner can at least be discussed in a more sophisticated way now, with decoherence and understanding what collapse of the wave function really is in a less crude way, or what the sophisticated operation is that replaces collapse of the wave function. So I don't think that consciousness is profoundly involved in the foundations of quantum mechanics.
I'm really sorry. The last question I would ask anyone.
Everybody loves questions.
Do you? I know it's not quite a question that is supposed to ask in a polite audience, but still, do you believe in a kind of a definite reductionist approach to the world? So, do you think that at the end of the ends, not our generations, but in say 10,000 years, will be able to, you will be able to describe the world from the point of view of those fundamental theories.
Well, let me say
everything that we have here, us, our stupid, my stupid questions, the world that is around us, consciousness.
Well, I think there are two very different senses in which that question can be addressed that are often conflated, but they're very, very different. One is, well, crudely speaking, one is finding the laws, and the other is understanding their implications and applying them to the world. Newton, in the early days when he was describing his procedure, talked about analysis and synthesis very beautifully. I think it's a much nicer description than reductionism. But analysis is understanding the basic laws, and then having done that, you face the task of synthesis, which is building up a description of the world. Now, I would say you don't have to wait 1,000 years. We know now the equations well enough to have stable foundations for chemistry, biology, biochemistry, geology, engineering, medicine, psychology.
Psychology?
Yes, the equations, not necessarily the concepts, but in other words, I don't think fundamental discoveries in physics are going to help you solve any psychological problems. Put it that way. Now, because why do I say that? Well, we have this standard model that's been built up over centuries of accumulated investigation with mountains of data supporting it, testing it at extreme accuracy and also under extreme conditions like at the LHC or in applications to astrophysics, neutron stars or even black holes. And it works. So far it's been very difficult to find, well, impossible so far, basically to find a failure of it, even though people are very motivated to find a failure. They get Nobel Prizes and so on. Those conditions and that accuracy goes far beyond anything you need for biology or chemistry or engineering. So I think we have the stable foundations now, but I don't think that, and you know, your reaction is quite appropriate when you say psychology. No, having the laws doesn't mean you understand psychology. Okay, it just means that there's a program of understanding, using the laws we have, and studying the molecules, the particular reactions, the structures, and building up a description of what memory is, of what emotion is, of how thought processes work, that I think will eventually lead to understanding of psychology. I don't see any barrier to it, and I would be very, very, very surprised if it requires some new discovery at the LHC or in cosmology to understand psychology. I think physics has taught you everything it's going to teach you about psychology, to put it another way. Or fundamental physics, of course, you know. Physics of complexity might introduce new ideas. Yeah.
Okay, I just would like to add something to your discussion.
Yes.
I'm very glad about your comment because I'm very glad about your comment to this question because there were a Vienna Circle philosopher, Rudolf Carnap, who wrote 1915 Die Einheitswissenschaft, and the thesis was that first of all we have the basic is physics and we have to come up all the other theories. And so in the case that we have solved all the problem in physics, we can explain consciousness. And so thank you very much for your
let me add one thing that I should have.
I think in principle it will not be possible.
Yes, I think I should add one more thing. You can ask why should if the equations are complete as a description of the physical world, why shouldn't they explain psychology? And the point is that psychology, as we understand it here on Earth, is a product not only of physical laws, but also of particular events that happened in evolution, in condensing the Earth as opposed to Jupiter or other planets that are slightly different from Earth, where psychology might be quite different, right? And psychology of our near relatives like chimpanzees is quite different from human psychology, even though they obey the same physical laws. So there's no prospect at all, and it'll never happen, that you'll be able to just sit down with the fundamental equations of the Standard Model or string theory or whatever and derive a frog, because that's just not the sort of thing that's uniquely determined by the laws. Right.
You don't have to go to psychology. You can remain in physics and find out that the fundamental equations don't solve the 10-electron atom problem without additional approximations or ideas or concepts, not to mention collective phenomena and so on and so forth. So I guess that this...
Well, there's a lot to say about this. Another aspect is that...
Introducing psychology can model these ideas about complexity, because at each level you really have to complement your fundamental equations.
Yes.
And there's a whole discussion going on about this in physics. So, the question, are you in Anderson's, let's say, on the Anderson side, or the high-energy physics side?
Well, I think I'm more closely related to we discussed this at great length at dinner yesterday. I find myself much more sympathetic to Anderson than to some of my colleagues in high-energy physics. But another point I wanted to add is that not only are many of the facts of biology contingent on historical events, and so in principle can't be derived from equations of physics, but also there's a very well-known phenomenon, sometimes called chaos, sometimes called extreme sensitivity to initial conditions, that if you have equations and are trying to describe a reasonably complicated system, you find that in order to discover the behavior of that system in certain important details, you need extremely accurate information on its initial state. I mean, typically the laws tell you, okay, given the initial state, what's going to happen in the future. But sometimes you would have to know the initial state so accurately that in principle that it's totally impractical to make predictions. So then we need other concepts. We have to find invariants or things that aren't subject to that sensitivity.
Well, thank you very much to all of you. Thank you very much, Frank, for this wonderful discussion. I would like to encourage our students, our researchers to attend the ontology conference, that many of these things will be discussed there as well, and Professor Wilczek will be talking also in Chile Daleku. Some of the visitors maybe can use the opportunity to visit Chile Daleku on Saturday afternoon. And I would like to especially thank Professor Gomez Pin as the head of the Congress for having given us the opportunity to bring Frank here and enjoy his stay. He will be staying here the whole week, and I'm sure he will be looking forward to explain why knowing everything about the quark is not knowing everything about everything, as Feldman did, and he is closer to the sentence that the theory of everything will almost tell us nothing about everything we are interested in.
Well, I think
Thank you very much.